Hi, welcome to video series on operating system. Here we are discussing about CPU scheduling. Here definition: processors operating system use scheduling as a basic method to choose which of the ready in memory activities get the CPU. One of the most important resources in a computer system is the CPU, and efficient scheduling makes sure that resources is used to its full potential. Importance of CPU scheduling in operating system. First one is CPU utilization. Maintain the CPU as occupied as feasible. The scheduler maximizes system performance by minimizing idle time and efficiently allocating CPU time to process. And next one is throughput. And next one is waiting time. And next one is turn around time. Throughput increase the quantity of a task finished in a specified amount of time. Throughput effective management of the amount of time each process spends on the CPU. Productivity can be increased by finishing more operations. And the next one is waiting time. Cuts down on the amount of time process spends waiting to be performed in a ready quick. Algorithms that are good at scheduling can prioritize work such that important or time sensitive operations get done quickly and without delay. And third, around time. Reduce the amount of time needed for processor to finish from the start to finish. For both batch and interactive system scheduling helps controls and shorten the process time. And here you can see the responsiveness, fifth one. And in responsiveness, increases system responsiveness, which is crucial for interactive system in particular. By prioritizing using oriented tasks throughout scheduling system are kept responsive to user input and actions. Next one, here you can see the diagram of CPU scheduling. CPU have two types, primitive and non-primitive. In primitive, priority scheduling, longest remaining job first and shortest job first and job first. You can observe here. Here we are discussing about non-primitive scheduling. Here you can see the non-primitive scheduling diagram. Ready to quick and waiting and running, and last one is exit. Here you can see the definition of non-primitive scheduling. This particular scheduling strategy allows a process to continue running until it completes or enter the wait state. While it is operating, we are unable to stop it. And in process execution in non-primitive scheduling, when a process is chosen for execution and begins utilizing the CPU's non-primitive scheduling, it continues until one of the following happens. First one is process completion. The process finishes running and exits, freeing up the CPU to be used by the following process in the ready queue. Wait. The process delays the CPU of its own violation. The process enters a waiting state in this instant, and the scheduler choose the subsequent process from the ready quick. And here how the process operates. First one is ready quick and process A running and terminates or waiting. Here process running. First one is arrival of a process, second one is process execution, and third one is finishing or waiting. Arrival of a process. If the CPU is busy when a new process arrives, it is added to the ready quick. Process execution. When the CPU is available, the scheduler chosen process from the ready quick. Once a procedure is chosen, it continues uninterrupted until it is finished. Finish or waiting. The CPU is released when a process finishes or goes into a waiting state, at which point the scheduler chooses the following process from the ready queue. Here you can see the example for non-primitive scheduling. The well-known first come first serve algorithm is an example of non-primitive scheduling algorithm. In first come first serve, the order of execution is determined slowly by arrival time. The first person to arrive gets served first, as the name suggests. Another illustration is shortest job first algorithm, which prioritizes the task that takes least amount of time to complete. Here, short job uses the CPU until is finished. The next shortest job job take over. And here, next one is primitive scheduling. Primitive scheduling is a kind of CPU scheduling that allows the operating system to switch the CPU from one task that is running to another. Here you can see the ready quick, running, exit, and waiting. Here you can see the diagram. And process interruption and transition to waiting state. In process interruption, there are steps: high priority process arrival, time quantum expiration, IO input and output event completion. In higher priority process arrival, the scheduler may permit the running process to give the higher priority process permission to run. If a new higher priority process shows up the ready quick time quantum expiration. Every process in a round robin scheduling scheme is given time slice or quantum. A process may be printed and returned to the ready quick if it takes longer than expected to finish input or output or event completion. If a process has a higher priority than one that is currently running, it may take produces over the waiting process after completing its IO activities or receiving the required resources. Transition to waiting state. The operating system carries out the following actions that proceeds to preempted. Save process state. All of the data related to the active process such as program counter, register and any other required informations are stored. Move to waiting or ready quick. The process is either moved back to the ready quick or to the waiting state, depending on the reason for preemption. Schedule a different process. The scheduler chooses a different process to execute on the CPU from the ready quick. Here you can see the diagram: ready quick, process A running, waiting or ready, select process B and process B running. Here example of primitive scheduling, round robin illustration of a primitive algorithm. As the name suggests, it plays all the process in a round or circular sequence, giving the equal priority and time intervals. Another illustration is the shortened remaining time first algorithm. This favors the process with the least amount of time left to finish. Thank you.